Now we have situations where we want to check the correlation between two things. Now, looking at the fact that as x is increasing, y may be increasing. That's a possibility. As x is decreasing, y may be increasing. That's another possibility. So in this case now, x is increasing, y is also increasing. That's generally, here, if you check here, it's not the case. The issue is that in reality, sometimes y may not increase every time that x increases, but what you may find majorly is that as x is increasing, y is increasing. For instance, x is 2, y is 4, x is 3, y is 5, x is 8, let's leave that one for now, x is 9, y is 7. So we're saying predominantly as one is increasing, the other is increasing. But sometimes you may find a few points that don't follow that kind, which is like an example now is the 2 we have here. It may not increase in its own sense, but generally we are seeing an increment each time that x increases, we are seeing an increment in y. Now, what we are saying is that we want to find out that, okay, is it that when a particular variable, maybe x for instance, is increasing, y is increasing, or as x is increasing, y is decreasing? For instance, it could be 2, 3, and maybe 4 here, but maybe y started from 8, and then it goes to 4, and then it goes to 2. This means that as x is increasing, y is decreasing. Whereas as x is increasing here, y is also increasing. Now, what we are trying to do in everything is to find a way to quantify the relationship between the two. And we do that using some formula that can give us a range between -1 and +1. So -1 and +1. So that just like your probability falls between 0 and 1, this time around, your correlation coefficient will fall between -1. We call the correlation coefficient R. That's the estimate. The population value is called rho. Don't forget that rho is a Greek alphabet. You can see that here. All right. So in that case, we have our R to be from between -1 to +1. It can take any value. You need to know that, and you need to remember that when it is +1, it is a perfect relationship, perfectly positive relationship. When it is 1, it is a perfectly negative relationship. Somebody needs to mute your microphone. Please mute your microphone. Please mute your mixophone.
Wow, mute your mic. Wow.
All right. So now we are looking at +1, perfectly positive relationship. I'm just using PPR it's not any special thing. Actually, I'm just the one writing it. Negatively positive relationship. So when it is -1, it is perfectly negative relationship, perfectly negative relationship. When it is +1, it is perfectly positive relationship. Now, when the correlation is from between, let's say, 0.7, okay, anything from 0.7 to 1, it is a strong relationship. But then, when it is maybe anything from 0 to 0.49, it is a poor relationship. It's not good enough. So from 0.5 to something around 0.69, it's a moderate kind of relationship. But it depends on how you want to define it. There are some standards. Some people give maybe up to 4 or 5 definitions to it. But I want you to be concerned about this one for now. It is strong, and also be concerned about this one, that it's poor here. All right. So but generally, let's be concerned about this. The definition for strong relationship is acceptable to everyone within this range, 0.7 to 1. Okay. So please take note of that. Now we are done with that. So let's now we looked at a particular correlation before now, a particular type of correlation, and it's called the Spearman, it's called Pearson's correlation. So that's the correlation that was given to us by Pearson. But we want to look at another correlation today. It's called Spearman's rank correlation. So this is an example of a rank correlation. I'm going to define what we mean by a rank correlation soon. Now, that's what we are looking at today. A rank correlation has to do with coding your variable, or rather ranking your variables. So if you have variables this time around, you are no longer doing what you did during the Pearson's correlation. This is Pearson's correlation. Actually, it consists of looking for some summations. These are the summations actually, but let's look at the example that was taken. We had to look for the correlation between these weight and calorie intake. And then when we did that, we got the solution. It looked something like this. All we had to do was to sum everything under y. That gives us this value. Sum everything under x gives us this value. Sum everything under. All right. Now x and y. Xy means x times y. So 2 times 60, 120. 1.3 times 45 gives us this. And then when we are done with doing that for all of them, we sum up. We get this value. Then we square x. Our x. When we square x is 2 here, so x squared is 4. X is 1.3 here, so x squared is 1.69. And like that we continue. When we are done, we sum everything up. And then it gives us 21.99. Do we get that, please?
Yes, sir.
All right, so we continue. We square y also. 60 square gives us 3,600. 45 squares gives us 45 square gives us 20,025. And then when we are done for all of them, we sum. We get this. Now, by putting everything that you have here in their respective places, you get 0.49. And we discussed something called coefficient of determination. That's the square of the correlation coefficient. Now, whereas your R was 0.7049, your R square coefficient of determination is 0.4969. Now we continue that way, and we did what we call hypothesis testing. And when we do the things that we have to do there, we eventually get to reject H naught. And then we say, this correlation is a coefficient is not significant. That means we cannot use it on the population, but it's just limited to the sample we got it for. All right, now let's move on. We have seen that. Now we want to look at rank correlation. Everything we saw there is just in a bid to obtain a coefficient that can tell us the kind of relationship, the strength and direction. So if it is negative in the correlation thing we're talking about, if the correlation is negative, then it means that as one variable is increasing, the other is decreasing. So maybe x is increasing. Permit me to use this as to show that x is increasing and y is decreasing. Or it may be vice versa. X is decreasing and y is increasing. Now, these are two possible ways. So, but when it is positive, then it means that as x is increasing, y is increasing. So if you say as x is decreasing, y is decreasing, that's also that's also, I don't think you get anything outside positive, because it means as one is changing direction, the other is changing direction. So which means they will have, the line may come from maybe up, but they will have a line that looks something like this. For a positive correlation coefficient, the line will look something like this. For a negative correlation coefficient, the plot between the two variables, I mean x, let's put y here, y, and then you have x, y, and then you have x. So this is negative r, that's negative correlation coefficient, and then positive correlation coefficient. Now, that's how you're going to have it. So in this case, whether x is decreasing and y is decreasing, or x is increasing and y is increasing, meaning that they're going along the same direction, you are going to have r to be positive. But if as x is increasing, y is decreasing, or x is, as x is increasing, y is decreasing, or x is decreasing, y is increasing, then you are going to have a negative correlation coefficient. Now, that being said, we can now look at our rank correlation. Now, what we did before was to use the exact values that we got from our data, but now we want to rank the data. We don't want to use the data as it was. And so the reason for this is that sometimes you may not be able to use the exact values that you obtained from your variables, depending on the situation at hand. There are some tests that we call non-parametric tests. You may not understand that for now, but just understand something here. We are ranking. We are not using the exact values. We obtain ranks. So let's look at the example we took the other time. Okay. Now, the formula for your rank correlation, let me write that. Rank Spearman's rank correlation. Okay, so your R is going to be something like sorry, please. Your R is going to look something like 6 summation. So it goes on like that, and this time around, what we are going to have as our correlation, as I said before, will be obtained from the rank stuff. And so it's going to look something like this. Don't worry, even if you're confused, maybe by looking at the formula, you don't have any issue. You are going to do well because you understand it, I believe. But the only thing is that you need to follow well with what we are doing. So 6 summation, then we have what we call the deviation, and that will be squared. So let's call this, some people call it small letter d, but in this case, we can call it small letter d. di. In case you're checking some other book or something, and then you see, and then you have n multiplied n squared minus 1. Now, this is what it's going to look like. You'll be getting this difference in a way that we're going to be looking at shortly. Now, where you're going to define all of this now, and there is a deviation, as I said before. Okay. And these are coming from the ranks. So it's better that we illustrate illustrate this than just write that. But let's look at this. So di will be equal to rank of x xi, let's put that xi minus the rank of yi. Now, for some of you who may be asking, what if we do it the other way? Maybe rank of yi minus rank of xi. Well, the good news is that you are squaring your d. So even if you do it that way, you'll be correct. It's just, the only thing is that make sure that if you are doing yi minus xi, that's rank of yi minus xi, make sure that you are consistent with it all along. That's just the only thing there. But whichever way you do it, even if it's not just good for you to mix it up, because you're going to write a formula and what you are writing should tally with what you are doing. And in any case, that's just going to be it. So we go on. Now we have this. Let's look at the example we took before. Now, assuming that just like before, you are told to find you are told to find the correlation coefficient for weight and calorie intake using the method using Spearman. Okay, let's just say obtain the correlation, the Spearman rank correlation coefficient. Now, when we don't need to obtain any sum in this case. So let's go on with the solution. Now, we like to rank the two of them. Here, we will be ranking the two variables. And what do we mean by rank? We want to check how they occur. I mean the order. Sorry, I'm trying to. Okay. All right. So we are calling our X, we said the calorie is dependent on, calorie intake is dependent on, no, the weight is dependent on calorie intake. So this is our Y, this is our X, right? So permit me, I may take up these ones. But it's actually a good idea to make sure that you're writing what should be written there. So let's call this weight. Weight, and we call this our Y. We'll call this one our X, and actually this calorie intake. All right, now we can move this a bit here. So let's look at so the rank of Y, and then we look at the rank of so if you like, you may call this YI, rank of YI. So you call this, you're even permitted to change it to RXI if you like. But for now, I will leave mine as rank of what you need to define what you have. So it's better you just write rank I, but if you write R and then you put XI in bracket, then you need to define what R means. Say R means rank. So you don't need to write rank all the time again. Now we have it this way. Now we can yes, we can now look for the rank of the two variables. Now, basically what we are doing or what we'll be doing is actually to find the order in which maybe they are ascending. It's preferable that we use the ascending order. We're using that. Let's look at that now. 45 is the first number, right? Not of magnitude. What's the second one, please?
Yes, sir. 61. 60.
Then 61.
61.
Then which one again?
73.
73 and
73.
Finally 5.
82.
Okay, 82 rather. Now going on, starting in this one now, the first number is 1.3, right?
Yes, sir.
Then the second one is 1.7. The third is 2. That gives us 3. This is 3. And then this is 4. And finally, this is 5. Now that we have this, we can now take the difference between the rank. So DI, as we said before, is equal to rank. So what did I use the other time? Whichever one you have used will be correct. Whichever one you use will be correct, but I want to be consistent. Okay, why xi? I want to be consistent with what I've written before. Xi minus rank yi. Now I will be also giving an instance where you have ties in rank. For instance, in this case, we don't have that, but let's assume that here we also have 45. Okay, I think it's better to do that somewhere else. Let's assume that in any case, we're ranking our x and what we had for x was, or y rather, was 60, 45, and maybe 45 again, and then maybe, and they don't have to be in the same place. We may even have 61, we may have 82, and then maybe we now have 45. Now, the way you're going to rank that will be somewhat different. You need to do something. You need to do something, or else you may not be able to rank, or you may not be able to obtain a correct correlation coefficient. Sorry. All right. So let's do something here. Now, in this case, what you would have done is to say you start with 45, but because there are two numbers that have the same rank, you are going to rank the first one. I mean, you are going to rank them equally, but in order to obtain the rank, then you will take two numbers and then you add them and divide. What do I mean? You are going to say the rank of this ordinary should have been 1, and possibly this should have been 1 and this should have been 2. But because they are the same numbers, since they appear twice, you take 1, and then you take 2, and then you divide by 2. Now, if 45 had appeared 3 times, you would have taken 1 plus 2 plus 3 and divide by 3 rather. Do you understand that, please? Hello?
No, sir.
You don't understand. Now, whenever there are numbers that appear more, whenever there's a number that appears more than once, you count the number of times it appears. How many times does it appear? So you add from wherever you are already ranking. Let's assume that the last rank you wrote before you got to that number it could be any number. In this case, actually, it's the first number appearing. So I'll take a case where it's like that. So let's go back. In this case, it appears 2 times. So you take the first 2 ranks that you get. So the rank that you'd have given this and the rank that you'd have given this, if they appeared if 45 was different from this 45, let's assume this number was 46, you'd have given it a rank of 2, right? Right?
Yes, sir.
So you are going to take that 1 and 2 and divide by 2. The reason is because 45 appears twice. But the 45 had appeared 3 times. In this our data here, let's assume it appears 3 times. Then you are going to give each 45 that appears, you are going to give them a rank. But how do you obtain that rank? So this 45 will be given a rank of 1. Ordinarily, that's how it should be. This one would have been given a rank of 2. This one would have been given a rank of 3. So you are going to add all the ranks and divide by, this time around, a 45 appears 3 times. So you are dividing by 3. You are adding 1, 2, 3 and dividing by 3. Now, if 45 had appeared 4 times, so that you can understand now, 45, and then you had 45, and then you had 45, then what you would have done is to rank them. You give 1 here, 2 here, 3 here, 4 here. You are not going to write this rank on them, but you are trying to obtain a rank that you are going to give to all of them. Please don't forget about the cases. This case is associated with this one. All right. Now, the next case, this case here is associated with this one. The next case I want to give now is this one. It's associated with, you are going to say 1 plus 2 plus 3 plus 4. Plus 3 plus 4, all divided by 4. So if you don't understand yet, don't worry, you understand. So this one would have given us 1.5. So rather than writing 1 and 2 as the rank, which we do not permit in this Spearman correlation coefficient style, we are going to write 1.5, 1.5. In this other case, if you divide this should give us 6 divided by 2. The rank for this case now will be 2. This one will give us 2, please. 2 and 2. So all of them would have been ranked 2. Now, in the last case, when we divide this, we should get 10 divided by 4, that's 2.5. So all of them would have been ranked 2.5, 2.5. So all the 45 should have been ranked 2.5, 2.5, 2.5. So you'd have had to write 2.5, rank here 2.5, the rank here 2.5, the rank here 2.5, the rank here 2.5. Now, let's go on. If you are you understand it, it will only take a short while, you understand it. Now, let's assume that we had a number before 45. Let's assume we have 36 first. This is y. Now, remember, this will be 1 now. And this time around, we ought to have written, okay, let me, rank. We're talking about the rank now. Please permit me to use, I mean this rank here. This rank is what I mean, but I'm writing R just to save time. Now, the rank of 3 will be 1. The rank of 45, this time around, will be, what's the next rank you get? Ordinarily, this should have been rank 2, and this should have been rank 3. Is that true?
Yes, sir.
But because they are the same number, we cannot write 2 and 3 here. So just like we did before, the reason why we did 1 plus 2 divided by 2 the other time was because that was the first rank we took. 45 was the first number we ranked. But this time around, the first number we are ranking is not 45, it's 36. So the next rank should be 2 and 3. So the next ranks for the number should be 2 and 3. So we are going to divide these 2 by 2. That will give us 5 divided by 2. That should be 2.5. And so our rank, the rank for 45, anytime it appears, and it appears twice, will be 2.5. Now, so when we have done that, we can no longer continue with the the two ranks we have added and divided by. Don't forget, I tried to say that if we had 45 3 times, let's do it in this case also. Assuming that we had another 45, 36, 60, 45, 45, 61, 82, 45. Then what would have had? Okay, before I go on, assuming that we only have 245, the next rank we'll be taking will not be 3 again, it will be 4. So the next number that we should rank should be 60. So we write 4 there. We can't take 2 and 3 again. We are done with them. Do you understand that?
Yes, sir.
So we go on, and then the next one should be 5, and then the last one should be, that's 82 now, 6. Now, let's go on to a case where we have 45 here. 45 is appearing 3 times. If we have 45 again, then we would have taken 2 plus 3 plus 4 divided by 3. What are the numbers we have? We have 45 appearing 3 times, so we are dividing by 3. And we are taking the next ranks that starts from the first 45, which is 2. So 2, then you take 3, then you take 4. Why are we taking 2, 3, and 4? We are taking the ranks that should have been given to 45, each of the 45s, if they were different numbers. But because they are the same number, they are the same number, we are dividing by the number of times it appears. How many times? 1, 2, 3. And why are we adding 2, 3, and 4? That's the next set of ranks. We are adding these numbers because the next rank should be 2. And this same number appears 3 times. So we add 2 plus 3 plus 4. Do you understand that now, please?
Yes, sir.
All right. Now, we go on from there. But in the example we are taking, we don't have any such thing. So the next rank that should have followed now, 60 is the next number to rank. We will not write 4, we'll write 5. Because we are taking 2, 3, and 4. So we can't use them again. So we need to start with 5. We'll come 5. Then we come here. This one is 2.5. That's 45 actually. So 5. Then we'll come here. We'll write 6. Then this one will be 7. So please take note of that. Now we can move on. Now we have obtained our ranks, and please take note of the case in which there's a tie. So when a number is appearing more than once, we say there's a tie because the rank they will receive will be the same when a particular number is appearing more than once. Now we take the difference between them. 2 minus 3, okay, we are taking 3 minus 2. 3 minus 2 will be what? 1. 1 minus 1 will be what? 0.
0.
5 minus 4 will be what?
1.
1. So we move on. Now, so now the calculation can now be obtained. Okay.
By 3.
Hello, please mute your microphone. Please, thank you. Please mute your microphone if you have to discuss with somebody. Please. Now coming back here, we obtained our B when we were discussing the other time. So we said 3 minus 2 gives 1. 1 minus 1 gives 0. X minus y, don't forget, rank of x minus rank of y. Now, continue. 5 minus 4 gives us 1. 2 minus 3 gives us minus 1. We go on. 2 minus 3 gives us minus 1. And then 4 minus 5 gives us minus 1. And then when we square the ones we had obtained, 1 square gives us 1. 1 square gives us 1. 0 square gives us 0. 1 square gives us 1. Minus 1 square gives us 1. Minus 1 square gives us 1. So when we add all of these, we sum them up, we get 4. Now we come to our formula. It says 1 minus 6 times the summation of di's square, which is 4. and divided by n multiplied by n squared minus 1. And where n is 5, that's because we have 5 data points for each of, or observations for each of the variables, 1, 2, 3, 4, 5. So you can see that that's where we got our n from. Summation bi squared equals to 4, which we obtained from here. And then we fix all of that into the formula, and we get 0.8 when we are done solving. Now, that's not all. We now need to obtain something. Sorry, please. Okay. We need to obtain sorry. Codry, you want to ask a question? You ask your question. Just give me a moment, please. Let me finish. I will be done soon. All right. All right. I've written this somewhere else. I just want to take it, bring it here, and okay. We should get it. Now, Codry, you can ask your question. Ask your question.
Yes, good morning, sir.
Good morning. It's not morning, it's afternoon. Sorry, good afternoon. Okay, I'm listening to you.
At d square.
Yes. I'm listening.
Yeah. I mean, can we please go back to that d square?
I'm back there. All right.
Yes, thank you. Yeah. We said d equals to rank of x minus rank of y.
Okay. Oh, sorry.
Are we subtracting with?
Okay, I'm listening. I'm listening. Are we?
The same position, or we are just subtracting?
Randomly. All right. Codry, I couldn't get your question very well because of the internet, but if I understand what you are saying, we are not doing it randomly. Permit me to make a mark on what we are doing. This is rank of xi minus rank of yi. So we did 3 minus 2 here. 3 minus 2. What's the rank of xi? 3 for the first number. And what's the rank of yi? 2. So we did 3. All right. Just in case somebody else may
you need them.
This other one, it's 1 minus 1. And that give us 0. Codry, are you following?
Yes, sir, it's clear now.
Clear now. Okay. This is 5 minus 4 and is equal to 1. This is 2 minus 3. Oh, sorry, I'm putting that in this way. I'll fix that in a moment. It should have been 3 minus 2, 1 minus 1, 5 minus 4, 2 minus 3, 4 minus 5, and if you permit, you may erase these ones. Right equal to 1, equal to 0, equal to 1, equal to minus 1, equal to minus 1. Now, when we come back here, it now becomes Sorry about that. It now becomes 1, squared is 0, 1. So becomes 1, becomes 1. So this one is also 1. This, okay. So that's how we got 4. So if you are confused, shouldn't be confused again. We can continue. Now, after we are done with that, we need to look at the test of, we need to test the hypothesis about the correlation coefficient. And what we are trying to do is just to see if what we have obtained can be used to make conclusions. So when you, okay, that's it. So when we do that, we have a formula already. And when we fix our values, the value of R and N into it, we get 4.2820. We have a table value. I explained in the previous video how to obtain the table value. And then when you get the table value, actually the table value here is 0.05 is usually what we have here, but 5 is coming from the sample, the number of observations, which we have here to be 5. All right, so looking at that, we move on. Now when we fix everything, we end up getting 2.571, and because this is not the correct conclusion, because what we calculated is greater than the table value, we are going to reject H0. We reject H0, and we conclude that the correlation coefficient is significant. Is significantly different from 0. Now, the last one we did, which when we considered correlation coefficient, Spearman's correlation coefficient, it was a different case. Actually, what we calculated was less than the table value. And because it was less than the table value, we rejected H0. So since what we calculated is less than the table value, we reject H0 and conclude that the correlation coefficient is not significantly different from 0. Why are we doing that? We already have a pattern. We have something on ground already. And this is what we were told. Whenever we want to test the hypothesis about the correlation coefficient, we have to compare what we calculate using what's above here with the table value. And then we reject the null hypothesis only if what we have calculated from here is greater than the table value. And so in the case of the Spearman correlation coefficient, it is greater. It is greater than the table value. What we calculated for the t statistic here is greater than the table value, which is 2.571. So we reject H0 and conclude that the correlation coefficient is significantly different from 0. So that means we can use it to make conclusions. We can now say, okay, these two variables, X and Y, have a strong correlation coefficient between them. So X and Y, that means weight and calorie intake, have a strong correlation coefficient between them. So that's why you're seeing 0.8 here, a strong positive. So they have a strong positive relationship. So that's what we are saying. There's a strong positive linear relationship between weight and calorie intake. All right, so that is that about that. So with that, we are done with the Spearman correlation coefficient. Let's go to what we'll be doing next.